So as a result of the activity, a couple of things to keep in mind when we're talking about um, the sum of a series being a Riemann sum is that as we look at these non-increasing series and make it similar to, or rewrite it as a function so we can calculate the area, what we're looking at is taking the a sub first term and say, well, when I get to a sub 1, when I get to that, I wrote that wrong, when I get to the first term of the sequence, that's got to be the value a sub 1 out here. And so I better have a box already drawn by the time I get to that first term marker on the x-axis. So if I already have a box drawn, then I'm going to need to have that box right here. So this is the a sub 1 box for the Riemann sum. And so if this is the a sub 1 box, it's got to be there by the time I get to this first term. By the time I get to this second marker here, I better have 2 boxes. By the time I get to this third marker here on the x-axis, I better have 3 boxes. So I'm adding up 3 boxes, because adding up 3 boxes is the same as adding up 3 terms in a series. So if I got to match the number of boxes by the time I get to that number on the x-axis, then we must be doing right Riemann sums. Anything else, and you wouldn't be matching up the boxes. So it should be a right Riemann sum. It should then the actual sum, which is the physical adding up the physical meaning of a Riemann sum, the actual sum of those boxes then, as we add them up, is going to be what the sum of our series is. And the idea is that then this integral, in performing the integral test, this integral is, the value of that integral is an overestimate, in a sense, of the sum of the series. So if it's finite, we know the sum is something less than it. So we know the sum is also finite. If this is infinite, then we say the sum doesn't, we cannot determine the sum. And so we also notice that this transition occurs right here. Okay, so if we have p that is either 1, equal to 1, or littler than 1, we have this divergent behavior. And if we had a p that is bigger than 1, then we had this convergent behavior. And so with that in mind, then, I just kind of sketched everything that happens here that we did in the activity. We can see that, we start out with x to the 1 over x to the 1/4 power, which is this dark purple line. Pinching off is not that severe. We ended up with 1 over x to the 4th, which is the yellow line, or the yellow curve, and that's a very severe pinching off against that x-axis. So we went from infinite area to finite area. And in going from infinite area to finite area, we went from a converging sequence to excuse me, I said that completely wrong. We went from a diverging sequence to a converging sequence. And so that gets us a nice rule then for the p-series test that I just kind of stated up there. And so for our p-series test, all we're doing is looking at the value of the power. And so our p-series test is a test then, and it determines convergence or it determines divergence. It's again a test for both scenarios, just like the geometric series test is a test for both scenarios. The nth term test only tests for divergence. Some tests test for both, some tests just test for one thing or the other. So the idea is divergence is when we have p less than or equal to 1. Convergence is when we have p greater than 1. So now we're just going to look at some series then that look exactly, like that activity. So for instance, here we go with a series of 3 over n to the 5/3. So I have sketched in here this red dashed line, and so if we look at this as n equals 1, this value is 3, so we're up here at 3. And so we look at this blue curve, which is that blue curve here, which is 3 over x to the 5/3, and we look at this red curve here, which happens to be 3 over x, and we see that this is our transition point. This is something that's divergent because we're talking about a power of 1. This is something that's pinching off that's far more severe. So to complete the p-series test, we just kind of acknowledge here that we have a p that is 5/3, and 5/3 is greater than 1. And so that being the case, it meets the criteria. The series then converges because of p-series test. And that's really all we have to say about it. We've stated what the value of p is. We've stated the criteria. We know that that's the convergent criteria. This graph just kind of reinforces how severe the pinching is. So if we look at this next example here, we have a series that's kind of the value of the power isn't so apparent. So sometimes we can kind of hide the fact that this is actually a p-series test application by rewriting the power as something else. So this has a power of 1. This has a power of 1/2. So we must have an n to the 3/2 here. And so again, as this sketch here, this in function notation is 2 over n to the 3/2. And just as a comparison here, I also sketched in 2 over n, because that is our dividing line, that is our transition curve from diverging to converging. So we can see that this actual curve that it represents the series 2 over n times the square root of n, this actual curve is more severe. So in this case, our p-value is 3/2, which is greater than 1. And so this series then, and you can write it like this, or you can write it in the rewritten form, doesn't matter, converges again because of the p-series test.